Hello, welcome to my video presentation on the protection of an LV generator set and the downstream circuits. My name is Martin Hlavačka, and in this video I'm going to talk about generator protection, downstream LV network protection, the monitoring functions, and generator set parallel connection. Most industrial and large commercial electrical installations include certain important loads for which a power supply must be maintained if the utility electrical supply fails, either because safety systems are involved or because it concerns priority circuits such as certain equipment, the stoppage of which would entail a loss of production or the destruction of a machine tool, etc. One of the current means of maintaining a supply to the so-called priority loads, if other sources fail, is to install a diesel generator set connected via changeover switch to an emergency power standby switchboard from which the priority services are supplied. Generator protection. The diagram below shows the electrical sizing parameters of a generator set. The generator protection curve must be analyzed. Standards and requirements of applications can also stipulate specific overload conditions. The short circuit current is the sum of an aperiodic current and of a damped sinusoidal current. The short circuit current equation shows that it is composed of three successive phases: subtransient phase, transient phase, and steady state phase. Subtransient phase. When a short circuit appears at the terminus of a generator, the current is first made at a relatively high value of around 6 to 12 times nominal current during the first cycle. The amplitude of the short circuit output current is defined by three parameters: the subtransient reactance of the generator, the level of excitation before the time of the fault, and the impedance of the faulty circuit. The short circuit impedance of the generator to be considered is the subtransient reactance expressed in percentage by the manufacturer. The typical value is 10 to 15%. Transient phase. The transient phase is placed 100 to 500 milliseconds after the time of the fault. Starting from the value of the fault current of the subtransient period, the current drops to 1.5 to 2 times the nominal current. The short circuit impedance to be considered for this period is the transient reactance expressed in percentage by the manufacturer. The typical value is 20 to 30%. Steady state phase. The steady state occurs after 500 milliseconds. When the fault persists, the output voltage collapses and the exciter regulation ceases to raise the output voltage. The result is a stabilized sustained short circuit current. If generator excitation does not increase during a short circuit but is maintained at the level preceding the fault, the current stabilizes at the value that is given by the synchronous reactance of the generator. The typical value of synchronous reactance is greater than 200%. Consequently, the final current will be less than the full load current of the generator, normally around 0.5 of nominal current. If the generator is equipped with maximum field excitation or with compound excitation, the excitation surge voltage will cause the fault current to increase for 10 seconds, normally to 2 to 3 times the full load current of the generator. Calculating the short circuit current. Manufacturers normally specify the impedance values and time constraints required for analysis of operation in transient or steady-state conditions. Resistances are always negligible compared with reactances. This value can be compared with the short circuit current at the terminals of a transformer. Thus, for the same power, currents in the event of a short circuit close to a generator will be 5 to 6 times weaker than those that may occur with a transformer. This difference is accentuated still further by the fact that generator set power is normally less than that of the transformer. On the diagram, there is an example of priority services switchboard supplied from a standby generator set. When the LV network is supplied by the transformer of 2000 kVA, the short circuit current is 42 kA at the main LV board bus bar. When the LV network is supplied by the generator of 500 kVA with a transient reactance of 30%, the short circuit current is made at approximately 2.5 kA, at the value 6 times weaker than with the transformer. Downstream LV network protection. Priority circuit protection. Choice of breaking capacity. These must be systematically checked with the characteristics of the main source, which is MV-LV transformer. Setting of short time delay tripping current. For sub-distribution boards, the rating of the protection devices for the sub-distribution and final distribution circuits are always lower than the generator rated current. Consequently, except in special cases, conditions are the same as with the transformer supply. For main LV switchboard, the sizing of the main feeder protection devices is normally similar to that of the generator set. The setting of the STD must allow for the short circuit characteristic of the generator set. Selectivity of protection devices on the priority feeders must be provided generator set operation. It is necessary to check the proper staggering of STD settings of the protection devices of the main feeders with that of the sub-distribution protection devices downstream. Note: when operating on the generator set, the use of a low sensitivity residual current device enables management of the insulation fault and ensures very simple selectivity. Safety of people. In the IT and TN earthing systems, protection of people against indirect contacts is provided by the STD protection of circuit breakers. Their operation on a fault must be ensured whether the installation is supplied by the transformer or by the generator set. The monitoring functions. Due to the specific characteristics of the generator and its regulation, the proper operating parameters of the generator set must be monitored when special loads are implemented. The behavior of the generator is different from that of the transformer. The active power it supplies is optimized for a power factor equal to 0.8. At less than power factor 0.8, the generator may, by increased excitation, supply part of the reactive power. An off-load generator connected to the capacitor bank may self-excite, consequently increasing its overvoltage. The capacitor banks used for power factor regulation must therefore be disconnected. This operation can be performed by sending the stopping set point to the regulator or by opening the circuit breaker supplying the capacitors. If capacitors continue to be necessary, do not use regulation of the power factor relay in this case. A generator can supply at most in a transient period a current of between 3 and 5 times its nominal current. A motor consumes a current roughly 6 times greater than the nominal current for 2 to 20 seconds during startup. If the sum of the motor power is high, the simultaneous startup of loads generates a high pickup current that can be damaging. A large voltage drop due to the high value of the generator transient and sub-transient reactances will occur, with a risk of non-starting of motors, temperature rise linked to the prolonged starting time due to the voltage drop, and tripping of the thermal protection devices. Moreover, all the network and actuators are disturbed by the voltage drop. Restarting tips. If the maximum power of the largest motor is greater than a third of the power of the thermal motor, a progressive starter must be installed on this motor. If the sum of the power of all motors is greater than a third of the power of the thermal motor, motor cascade restarting must be managed by a PLC. If the sum of the power of all motors is less than a third of the power of the thermal motor, there are no restarting problems. Nonlinear loads. Nonlinear loads are mainly saturated magnetic circuits, LED lamps, electronic converters, computers, etc. These loads generate harmonic currents. Supplied by a generator set, this can create high voltage distortion due to the low short circuit power of the generator. The combination of a UPS and generator set is the best solution for ensuring quality power supply with long autonomy for the supply of sensitive loads. It is also a nonlinear load due to the input rectifier. On source switching, the autonomy of the UPS on the battery must allow the starting and connection of the generator set. UPS inrush power must allow for nominal power of the downstream loads and the power required to recharge the battery. The UPS rectifier can be equipped with a progressive starting of the charger to prevent harmful pickup currents when installation supply switches to the generator set. Harmonic and voltage distortion value depends on the harmonic currents generated by the rectifier, the longitudinal subtrahend reactance of the generator, and the power of the generator. As subtransient reactance is great, harmonic distortion is normally too high compared with the tolerated value for reasonable economic sizing of the generator. The use of a suitable filter is an appropriate and cost-effective solution. Harmonic distortion is not harmful for the rectifier, but may be harmful for the other load supplied in parallel with the rectifier. Generator set parallel connection. Parallel connection of the generator set, irrespective of the application type, requires finer management of connection. Parallel operation. As generator sets generate energy in parallel on the same load, they must be synchronized properly and load distribution must be balanced properly. This function is performed by the regulator of each generator set. The parameters like frequency and voltage are monitored before connection. If the values of these parameters are correct, the connection can take place. An insulation fault inside the metal casing of a generator set may seriously damage the generator of the set if the latter resembles a phase to neutral short circuit. The fault must be detected and eliminated quickly, else the other generators will generate energy in the fault and trip on overload, and installation continuity of supply will no longer be guaranteed. Ground fault protection built into the generator circuit is used to quickly disconnect the faulty generator and preserve the continuity of the supply, and act on the faulty generator control circuits to stop it and reduce the risk of damage. This ground fault protection is of the residual sensing type and must be installed as close as possible to the protection device as per a TNC or TNC system at each generator set with grounding of frames by a separate PE. This kind of protection is usually called restricted earth fault. Generator set operating as a load. One of the parallel connected generator sets may no longer operate as a generator, but as a motor. This may generate overloading of the other generator sets and thus place the electrical installation out of operation. To check that the generator set is supplying the installation with power, the proper flow direction of energy on the coupling bus bar must be checked using a specific reverse power check. If the fault occurs, this function will eliminate the faulty set. Grounding parallel connected generator sets. Grounding of connected generator sets may lead to the circulation of earth fault currents by the connection of neutrals for common grounding. Consequently, to prevent these currents from flowing between the generator sets, it is recommended the installation of a decoupling resistance in the grounding circuit. We come to the end of this presentation. Thanks for watching.